Hello there, Mr. Sutton here, bringing you the AB Calculus 6-7 Extra Practice number 3 solutions on total distance. For this calculator-based free response problem, we have a particle moving along the x-axis so that its velocity between times 0 and 16 is given by this v of t equals e to the 2 sine of t minus 1 function. So let's see, at time 0 the particle's at the origin, and our very first task is on these axes here just to sketch the graph of v of t from 0 to 16. So this is pretty straightforward. You just go on your calculator and graph this thing and then copy the graph over here. So let's take a moment to do that. So to begin with, I have entered the velocity function in my y equals under y1, and now I'm going to go to window so that I can get the same window they're using over here. And my x min of 0 is good. I'm going to do an x max of 16, and it looks like my x values, my grid lines are going by 4s. So let me make my x scale 4. And then for y's, I want to go from, let's say negative 10 to positive 10. And I want to make those go by 4s as well, just so I can have the same grid lines as they have over here. And now graphing that out, there we go. Something like this. So here's what I had on my grapher, and we're just going to basically copy that over here. So I come up to, let's see, about 6, I guess, and then back down, and all that happens before I even get to this first 4. Then we come back around here, and let me just draw this as I go, and we're doing one of these, down again, and we stop at 16. So there it is. For this part of the problem, they want to know during what intervals of time is our particle moving to the left, and then give a reason. So moving to the left means that the velocity here is going to be negative. If this thing's going on the x-axis, the negative direction is the left direction. So one thing it'd be nice to know is where my velocity is 0. And then if I can figure that out, I can just look at my graph and work around those intervals. So I could actually figure this out on the graphing calculator, but I have a feeling, since there's a sine of t involved here, that I'm going to get answers in terms of pi. So rather than take all that time and do all that work on the calculator, I think it's actually just faster to solve this just normally algebraically. So if I add 1 and I take the ln of both sides, I can write 2 sine of t equals 0. And this is basically like having sine of t equals 0. So sine gives you back a value of 0 when you plug in 0, pi, 2 pi, 3 pi, pretty much every integer multiple of pi, so all the pi's. But we only have to go out until 16. So let me see here. Out of all of these, I think 5 pi is as far as you need to go before you get to 16. All right, so now we're just going to take a look and see where velocity is negative. So here I am back on my grapher where I drew that graph. And it looks like this is going to be 0, pi, 2 pi, 3 pi, 4 pi. This is 5 pi right here. And it looks like velocity is negative between pi and 2 pi. That's our first interval. And then taking a look at the graph again, the only other place where velocity is negative is between, this is going to be 3 pi and 4 pi. Actually, that's not true. So 3 pi and 4 pi is the next interval. But if you look real closely at this graph, we're crossing the x-axis just before we get to 16 at around 5 pi. So from 5 pi to 16, that's the other interval where velocity is negative. Since velocity is negative on all of these intervals, that means our particle is moving to the left on all of these intervals. For this problem, we want to know the total distance traveled by the particle from time 0 to 4. So taking a look at my graph one more time, every time we cross the x-axis here, the particle is changing directions. So one way to do this would, of course, be to take the integral of each of these sub-intervals between the x-intercepts, and then just make sure you're taking the absolute value of all of them. The faster way to do this would just be to take the integral from 0 to 4 of the absolute value of velocity inside the integral like so. And then this will also give you the total distance. So let me just do that on the calculator. So to do this, I'm going to pull up my integral with math 9, and I'm going from 0 to 4 on that. Inside, I need the absolute value of velocity, so I'm going to do alpha window, pull up this little submenu and pick absolute value. And in here, my velocity function, remember I stored that as y1 in my y equals. So if I do alpha trace and pull up my y equals menu, that gives me a choice of y value or y functions here. I'm going to pick y1. Again, that's where I stored my velocity. And we'll do dx over here for the differential. Press enter. And it might take a little while because we've got some back and forth going on with that graph that the grapher has to account for. So now we have 10.542, and that is our total distance traveled. There's no units on this, so this is good enough. For this last part of the question, they want to know if there's any time between 0 and 16 at which the particle returns to the origin. Justify your answer. All right, so to figure this out, I'm going to go back on my grapher and take a look at the graph that we had that we've used so many times here. Now, since this is the graph of velocity, that means that the area underneath the graph, or between the graph and the x-axis, is giving us distances traveled, either to the right or to the left. So this positive area here is distance to the right, this negative area is distance to the left. We notice that there's a huge distance to the right here, followed by a smaller distance to the left, followed by a huge distance to the right, which is identical to that first distance, followed by an equally small distance to the left, and this pattern just keeps going over and over again, since this is, when you get down to it, basically a trigonometric function. So in order to actually, so it doesn't look like our particle is going to return to the origin. I mean, you're taking a huge step to the right, you don't offset that going to the left, and then you take another big step to the right. So we just need a way to just prove this. So I'm going to start by finding the area of this first interval here from 0 to pi. Then I'll find the area from pi to 2 pi, and then I can just talk about how we're just repeating that over and over again. So first, let me find the area, the integral from 0 to pi of my velocity. So here we are, back on the calculator, running those numbers. And notice I'm just using y1, not the absolute value of y1. I just want the velocity itself. So integral of that gives us 10.107. And then let me find the integral from pi to 2 pi, because that's the next part of my argument I'm about to make here. So this is a little bit easier if we just yank the input from before. And now I'm just going to go back and replace the 0 with pi. And pi I'm going to replace with 2 pi. And enter. Gives me negative 2.067. So we initially start out with moving 10.107 to the right. Then we follow that up by going 2.067 to the left. And then we go 10.107 to the right. And we keep alternating back and forth between these. Since you're going more to the right each time than you are going to the left, your particle is never going to return to the origin. For this no calculator free response problem, we've got a particle moving along the x-axis with a velocity for positive or 0 times given by this v function here. We want the acceleration of the particle at time 3 as the first task of this problem. So acceleration is just the derivative of velocity, and we have the velocity right here. So I just need to take the derivative of this, so I'll write a of t equals v prime of t, and then I just need to plug 3 into that. So because I don't have the calculator to use on this problem, I actually have to figure out what v prime of t looks like algebraically. So this is going to be an exponential function. This 1 is going away because it's a constant, and then we have e to the something, or e to the 1 minus t, times a tail of negative 1, because that's the derivative of 1 minus t. So when the dust settles, negative e to the 1 minus t. So just have to plug 3 into that. And you could leave it like this. You don't really have to simplify it. Or you could make this negative e to the negative 2. Either way. For this part of the problem, we want to know if the speed of our particle is increasing at time 3. So to figure out if we're speeding up or slowing down, we have to take a look at the signs of velocity and acceleration and see if they are working with each other or against each other. Let's deal with velocity first. So that would just be v of 3, which is just going to be negative 1 plus e to the 1 minus 3. So does this thing come out negative or positive? Well, this is really e to the negative 2, which is 1 over e squared, which is a number that is less than 1. So if I have negative 1 plus something less than 1, that has to come out negative. And now the acceleration at 3, we actually found that in part A. Remember, that was just negative e to the negative 2, which comes out negative because you have a negative in front of an exponential function. Since velocity and acceleration at time 3 both have the same sign, since they are working together, that means our particle's speed is increasing at time 3. For this part, we want to find all t values at which the particle changes direction. So for this, we need to figure out where the sign of velocity is changing. And again, since we don't have a calculator, we're going to have to do this by hand. So let me start by setting velocity equal to 0 and solving. So we have v of t, which is all this stuff, equals 0. And let me just add 1 to the other side. Take the ln of both sides. That'll get rid of the e. So I have 1 minus t equals 0, because ln of 1 is 0. And then that means t must have a value of 1. So this is the only possible place where a velocity could change sign, so the only place where our particle could change direction. We don't know for sure whether it does or not. We're going to have to use some sign analysis to figure that out. So let me set up a v line here. And I can start with an endpoint of 0 because we're not supposed to plug in times that are less than 0 anyway, according to this function. So we've got 0, we've got our sole critical value of 1. And now we have to test some things out. Let me try plugging in, I don't know, 1/2. Why not? So I'm plugging that into the v function up here. This is going to be e to the 1 minus 1/2, and with a negative 1 out in front. So this is really negative 1 plus e to the 1/2, which is negative 1 plus the square root of e. Well, what's the square root of e? I don't really know. But since e is a number that's bigger than 1, the square root of e also is bigger than 1. So I have negative 1 plus something bigger than 1. That has to come out to a positive number. Now, something bigger than 1 over here for our sign analysis, that would be, let me try 3. Whatever you want to use. It doesn't really matter. So we've got negative 1 plus e to the, and we already actually did this before when we were analyzing acceleration. This is really e to the negative 2, which is 1 over e squared, which is a number that's less than 1. So added to this negative 1, this is all going to come out negative. And we, in fact, saw that the velocity of 3 was a negative number back in part B anyway. So we kind of already did this. So I noticed that velocity changes sign only at time equals 1. Therefore, the particle changes direction at time 1 only. For this last part of the problem, they want us to find the total distance traveled by this particle over the interval from 0 to 3. So if I just took the integral from 0 to 3 of velocity, that would give me the displacement. And if I didn't have any direction changes, it would also give me the total distance. Unfortunately, as we saw back on part C of this problem, we do have a direction change at time 1. So because of that, we have to take the integral from just 0 to 1 and add that to the integral from 1 to 3, and then we need the absolute value of both integrals to make sure we're not doing any negative distance. So then I'm going to do integral, absolute value of the integral from 0 to 1 of velocity, v of t dt, plus absolute value, integral 1 to 3 of velocity. So let's see here, antiderivative of the velocity function. This is going to be negative t minus e to the 1 minus t, because it's e to all this stuff divided by the negative 1 tail there. So there's my antiderivative evaluated from 0 to 1. And we also have pretty much the same stuff, but evaluated from 1 to 3 being added on there. And both of these get their own absolute value. Okay, so we've got all this stuff with 1 plugged in, and this is all inside one big absolute value here, minus all this stuff with 0 plugged in. So that's all inside a single absolute value. And now inside my other absolute value, I have this stuff with 3 plugged in, minus this stuff with 1 plugged in. And at this point, because I've got all constants, I can actually stop and be done. I do not have to simplify this if this is the real AP exam. However, it's not. So this is just a homework sort of explanation. So how about I just go ahead and simplify this just for fun? So right here we have negative 1 minus e to the 1 minus 1. Well, this is really e to the 0, which is 1. So we're doing negative 1 minus 1. That's going to be negative 2. Over here, this is going to be, let's see here, 0 minus e. So we have a negative e, but we're subtracting that. So this is really a plus e, and that's all inside one absolute value. In the other absolute value, this is negative 3 minus e to the negative 2. And then over here, let's see, this is negative 1, basically minus 1 again, so negative 2, but we're subtracting that, so this is now going to be positive 2. We having fun yet? Let's keep going. These absolute values have to get evaluated now. So remember, the absolute value gets applied after everything gets added together. So over here, e is actually bigger than 2. So if you do negative 2 plus e, it's going to come out to a positive number. We don't want to change that. So to get rid of this absolute value, we are just going to accept what is already inside here, negative 2 plus e. Over here, I need to simplify. So negative 3 plus 2 is negative 1. Negative 1 minus e to the negative 2 clearly is a negative number. So I just want the positive version of everything in there. Since everything is negative, I'm just going to make everything positive. So I'm going to do plus 1 plus e to the negative 2. And just to finish this off, we have negative 2 and 1 adds up to negative 1. So we have negative 1 plus e to the negative 2. Fully simplified.